Hello, my greetings to all attendants to this online presentation for the 16th SDEWES Conference in Dubrovnik 2021. My name is José Ferreira. I work in the Catalonia Energy Research Institute. I am in charge of the life cycle studies for the energy technologies in order to improve the sustainability of the products, services, and processes. Today I will present you the work which title is the life cycle analysis of a cobalt-free lithium-ion battery to support the renewable energy transition. This is the outline. Firstly, I will give you an overview of the Cobra project, which study is involved in this project. And then I will give you an introduction about the environmental concerns related to the batteries for the electrical vehicles. I will explain you briefly the concept of the life cycle assessment. And finally, I will give you the preliminary results about the life cycle analysis of cobalt-free lithium-ion battery. Focus on two developments for cathode, the approach 1 based on lithium nickel manganese oxide, and the approach 2 which is based on lithium nickel aluminum manganese oxide. In addition, I will give you a result related to the comparison between the commercial cathode and nickel manganese cobalt versus the approach to the developed in this study. Cobra is an European project which objective is to develop a novel cobalt-free lithium-ion battery technology in order to overcome many of the challenges faced by the electrical vehicle batteries in order to enhance of each component in the battery system in a listed manner. Basically, the chemistry of this battery is consisting of a lithium nickel manganese oxide cathode in combination with a composite anode based on a nanometer silicon and graphite as active particles. This project is financed by the European Commission under the program Horizon 2020. The project started last year and it is expected to finish 2023. And basically, the scope of the project is to develop the battery pack in order to be validated on automotive electrical vehicle testing. This is the consortium of the project. As you can see here, we have several companies, industrial engineering and research technology organizations, academic sector, and battery manufacturers. All of this consortium is involved in different European countries. From IREC, in particular from the Energy System Analytics Group, we are involved in the project in order to calculate the environmental impacts related to the solutions of the project using the life cycle assessment methodology in order to provide the guidelines for the eco-design aligned with the circular economy strategies. Well, as you know, the transportation sector has increased their emissions along in 2020 year. These emissions represented more than a quarter of the total greenhouse gases emissions in the European Union. This is why the electric vehicles is the main technology in the transportation sector in order to reduce these emissions. The batteries are the main core of this technology, and these batteries have important role in the transition, in the renewable energy transition. The battery, the lithium-ion battery technology implies to use different raw materials such as lithium, cobalt, nickel, manganese, and graphite, most of which are categorized as critical materials. This is these materials can bring environmental impact throughout the battery supply chain. This is why it is very important to address the entire life cycle in order to be able to assess the sustainability of the electrical vehicles. Regarding our findings in the literature and studies, we can see that the lithium, manganese, nickel, and natural graphite have moderate reserves to cover the expected 10% share of the electric vehicles in the global fleet in the next year. However, these reserves are not enough in order to cover the expected increase in demand. And on the other hand, if we consider an extreme scenario for 100% electrification of the world's vehicle fleet under continual ground conditions, having enough reserve of cobalt and potentially lithium is unlikely. In addition, according to our previous studies and literature, we have found that the cobalt and nickel, for example, increase significantly the environmental footprint of the lithium-ion batteries. On the other hand, the cobalt is extracted mainly from the Democratic Republic of the Congo, which is a region historically characterized by political instability and social impacts in the mining sector, involving issues related to the child work, safety mining conditions, involving many illegal extractions and uncountable deaths. The life cycle assessment methodology allow us to quantify the impact of a product throughout its life cycle, including the raw material extraction, manufacturing, and use and end of life. We can focus on the life cycle assessment study in three different focus or scope, for example, from the cradle to grave to cradle to gate and gate to gate. Even we can include an additional scope, which is the gate to the end of life. Methodology coming from of the philosophical concept named life cycle thinking, but it was the standards, the ISO 40014 and 40044, which establishes the guidelines in order to calculate the life cycle impact of product. In these standards, we have 4 phases in order to complete the analysis. The first step is to define the goal and the scope. Then we have to make the inventory analysis in terms of the materials and energy input and outputs. And then we have to convert this inventory and environmental impacts using different methods and using different environmental metrics in order to obtain the results which we will use it for the interpretation in the last stage of this methodology. This stage are very interactive between them. We come back to other stage depending on the redefining of the goal of the scope, or maybe we have to detect some improvement in the inventory, or maybe it is necessary to update the databases in the impact assessments. But at the end, we need to have the final results in order to provide the conclusions and recommendations. This methodology allows us to inform decisions and policies in order to reduce the life cycle impact of the product. And this methodology can support the product development and improvement in a company to make strategic planning, collaborate with the public policy making, marketing, benchmark, and this methodology is used in order to report the eco labels and product declarations. We'll start with this explanation of the study. The goal and scope was defined as to explore the environmental impacts related to the production of a cobalt-free lithium-ion pouch cells in its early research stage. This preliminary study it will be useful to develop the battery pack in the future for the vehicle. The study is focused on two cathode approaches, as mentioned before. The approach 1 is based on the lithium nickel manganese oxide, and the approach 2 is based on the aluminum doped oxide. Is similar to the approach 1, but the powder is doped with aluminum. This is the system boundaries, and you can see in this slide we have made the study from the raw material extractions and the component production, including the cathode, anode, electrolyte, and separator, and the cell production. The other stage belongs to the life cycle of the battery, was not included in this study, and the functional unit is defined as one pouch cells produced. On the other hand, as mentioned before, and we made a preliminary study about the comparison between the commercial nickel manganese cobalt cathode compared to the cathode approach 2. For this specific study, we have defined the functional unit as 1 kilogram of powder. You can see in this slide the life cycle inventory. In this table, we can find the different materials used to produce the cathode, the anode, the electrolyte, and separator. Basically, the difference between the approach 1 and the approach 2 was the binary used. In the approach 1, the binary user was the sodium alginate and using water as solvent. For the approach 2, the binary is confirmed by the polyvianidine fluoride, and the solvent used in the approach 2 is constituted by the methyl pyrrolidinone in this approach. And are the main difference between this approach. I have to say that the availability of the foreground data for components and materials was obtained from the developers involved in this research. On the other hand, in the background data to calculate the environmental impacts are obtained from Gavi datasets and EcoInvent datasets, as well as from existing scientific literature. We have included in the model the transportation from the material extraction to the manufacturing using the standard distance taken from the EcoInvent modeling. And this are the environmental impacts categories used in order to measure the environmental behavior of these approaches. You can see in this table, for example, we have the climate change category or global warming potential, which unit is the kilogram of the CO2 equivalent. Or we have another metric such as the primary energy, which is measured in megajoules. This category quantify the quantity of the energy per functional unit, increasing energy consumption from the renewable and non-renewable energy source. You can see other metrics related to the toxicity, the human toxicity, and ecosystem damage, for example, for the acidification, eutrophication, etc. So we use the software Gavi in order to calculate these metrics. And the methods used in the environmental impact were the CML method and primary energy demand from renewable and non-renewables. And when we do life cycle assessment, it is important to provide the assumptions for the model. In this case, in the LCA, we have included the estimations for the mass of the reactants or input materials for the production of the active material for cathode from the stoichiometric equations, whatever data was insufficient or not available. For the electricity generation, we used or we assumed the electricity mix for the European region, and the material and energy flows. So this is important to remark that the material and energy flows developed in this study are subjected to large uncertainties because the preparation techniques of component materials and under the developed are lab scale. So that means that this study cannot reproduce an industrial scale. Well, this is the first results that we have. You can see that the environmental performance to produce the cathode, anode, electrolyte, and separator for the pouch cells are compared for the approach 1 and the approach 2. We can see that the approach 1 has lower environmental impact through all impact categories. We can see difference ranging between 2% to 17% along of the all categories. If explore the environmental impact by component, we can see that the cathode is the dominant component throughout of the impact categories analysis, as you can see in this picture. For example, we can see the acidification potential has a high environmental impact for the cathode. Or for example, for the global warming potential, the cathode has a high environmental impact. similar for the primary energy demand, for example. Um, then, if we made the breaking down of the stage, we can see that the environmental impact for the cathode by materials. The active material has the main contribution of the cathode in all categories, as you can see in the blue bars in both approaches. Then we have the aluminum foil is of some relevance as well for both the approaches. In particular for the human toxicity potential category, as you can see in the orange part of this bar. On the other hand, we have the PDBF binder used in this approach too, which has an important contribution of between 12 and 25%, mainly in the ADP element category or abiotic depletion potential elements category, in eutrophication potential and human toxicity potential and or depletion potential. If we focus on the abiotic depletion potential elements, we can see that the environmental materials and PDBF binder are the main material responsible for the higher impact in the cathode approach. It is important to remark that the active material in the approach 1 showed a slightly higher contribution, around to 0.5%. So here the conclusion is to say that the binder is the responsible for this higher environmental impact in the approach 2 compared to the approach 1 in this ADP element category. Well, if we look at the distribution by materials in the active material production, we can see in this cake that the nitrate lithium and the ADTA are dominant in the abiotic depletion potential elements category. All of them contributing little more than 50%. On the other hand, we have the nitrate manganese exhibiting a contribution of roughly 14% for the same category. This is for this category for the abiotic depletion potential element, but in the other environmental category related to the depletion of the resource, we can see that the surplus orange potential, the lithium, the nitrate lithium has a similar contribution for both categories. However, the nitrate nickel has a higher contribution, around 50%, in the surplus orange potential category, while its contribution in the ADP element is around 10%. If we look at this is two categories which are related to the energy consumption, we can see that both the global warming potential and primary energy potential, and primary energy demand has important contribution, around 85%. This is contributed to the largely renewable resource flows in the PAD category due to the electricity needs assumed in this study. I mean, if the electricity mix study used in the LCA, as mentioned before, is for the region, for the European region, and we can see, for example, for the primary energy demand, the energy of non-renewable resource flows contribute largely to this category, because we have here important contribution for the lignite fossil fuels, for example, hard coal, natural gas, and uranium in the nuclear energy source. On the other hand, we have the presence of the fossil fuels being around 40% of the electricity mix, contributing largely within the global warming potential category. For the study of the comparison between the commercial nickel, manganese, cobalt, and approach 2, we can see for these specific environmental categories that the global warming potential and primary energy demand are the categories reflecting the highest impact for the approach 2. Compared to the nickel, manganese, cobalt cathode. It can be attributed to the high energy consumed to produce the active material for approach 2. The approach 2 shows less environmental impact in the total biodepletion potential elements, and the surplus or potential categories are around 30%. It is important to remark that the small batches will exceed higher energy consumption per kilogram of powder, so it is necessary many steps in powder consumption happening per patch rather than per kilogram. So this implies that the energy consumption will go down when the size of the patch is increased, or when the patch production takes place on the commercial scale or industrial scale. On the other hand, the energy consumption is also depending on the calcination temperature of the material. In this graph, we can see for the category of the surplus or potential that the active material approach 2 has lower environmental impact when compared with the nickel, manganese, cobalt power. This is attributed to the higher impact of the hydroxide, nickel, manganese, cobalt as subcomponent to produce this cathode. It is around the 87% of the total impact of the nickel, manganese, cobalt. If we see the materials required to produce this component, the hydroxide, nickel, manganese, cobalt, we can see that the sulfate cobalt component is the main responsible for the high impact, contributing around 17%, followed by the sulfate nickel with 22%. If we explore in the non-renewable element flow for this component, we can see that the non-renewable element flow in this category of the surplus or potential, the nickel, manganese, cobalt production shows that the cobalt is the element contributing sustainability, so it's substantially, around 68%, and both metals, nickel and lithium, account for burden of 25%. So we can see that the difference when we use the cobalt in a cathode, and when we use or when we don't use cobalt in a cathode, which bring us less environmental impact. In a similar way, if we explore the abiotic depletion potential, we can see that the components, in this case, the components, the sulfate, and nickel, and manganese, the sulfate, manganese, and sulfate cobalt, are the main contributions in this category. The difference between these two categories, the ADP, the abiotic depletion potential, and surplus or potential category, is the difference is the modeling of the methods, because the first one is a method developed by the CME-L approach. On the other hand, the surplus or potential is developed by the recipient method. And they consider different approaches. For example, the ADP element not consider the scarcity aspects, while the surplus or potential category, the method of the recipe consider the scarcity aspect. For that reason, we have different results. Well, the main remarks can be said that for the approach 1 and approach 2 in this study is that the approach 1 showed the best environmental performance when compared to the other one. For both approaches, it is very clear that the active material for the cathode production has the higher environmental impact in all categories. This is why it is very important to focus in this component in order to provide a design of the cathode with a lower environmental impact. In addition, we have detected that several materials have been identified in the battery cell, which have remarkable impacts depending on the considered category. For the energy consumption to produce the active material is dominant when focusing on the global warming potential and primary energy demand categories, which is due to the presence of the energy resource in the electricity mix of the European region. For the approach to comparison with the commercial nickel manganese cobalt power production, we found that the active material approach 2 has lower environmental impact in the surplus or potential indicator when compared to the nickel manganese cobalt power in the same metric. This is attributed mainly to the absence of the cobalt. And regarding the global warming potential and primary energy demand, which are related to the energy consumption, this is category reflecting the highest impact for the approach 2 compared to the nickel manganese cobalt. This is attributed to the high energy consumed to produce the active material approach. Finally, we can say that we have more work to do in this development of this kind of the lithium-ion batteries, and for that reason, this LCA study only provides a preliminary basis on the early design stage in order to try to obtain a cobalt-free batteries matured and therefore extending the life cycle study is very important in the future. Consider the cradle to grave perspective in order to know the big picture of the life cycle stage for this new solution. Thank you very much, and you can provide your questions during the different days in the different sessions through online, and it will be a pleasure from my side to respond any comments, any observations that you can have. Thank you.